Good morning and good afternoon. Thank you for joining us today. My name is Joanne Ferrara. I'm the Marketing Director at Dymedso, and I'll be your host for today's webinar for part 2 of the 2-part series on the impact of sound on airway clearance. Today's presentation will be given by Don Sizemore, President of D&D Medical, a Dymedso business partner. At the end of today's presentation, we will have a brief Q&A. Please type your questions in the Q&A panel. We are also recording today's session and will make it available to you on our YouTube channel. And now I'll turn it over to Don.
Thank you, Joanne. And welcome, everyone. Welcome back to part 2. If you will think back and remember, if you were in part 1, we covered technologies and looked at what has been used in the past for airway clearance, as well as we ventured into the latest technology. So I'm going to review a few of those things. The methods of airway clearance that we have on the screen there are the methods that we used in the past. And today we're going to review the latest in airway clearance technology, and that's the use of sound waves. We started our review with a statement about what sound is, and we said that it's an electromagnetic energy that creates pressure waves in the environment that it exists in. We also discussed that we are going to use 2 of the characteristics of sound to help us with airway clearance. Although there are many characteristics, and some of which we are going to learn today, there are 2 that we are going to use in particular, 2 methods to help us with airway clearance. First, we have to look at several characteristics of sound. The first thing that's really important for us to know that while we looked at a slide moments ago that showed the electromagnetic waves, of course, we can't see those pressure waves, but we do know that sound moves. In engineering, we say it is amorphous, it moves, and it moves differently through different mediums that contain sound waves. We also know that sounds are rated in terms of frequency. So one of the ratings you often hear is X amount of hertz or cycles per second. The scale that it goes through obviously goes up to kilohertz, megahertz, gigahertz, and so forth. So we go all the way up and down a scale that we call the sound spectrum. We also rate sound waves with power, and we call that rating decibels. Okay, so to give you something to relate to, a siren on a fire truck or a police car has 105 to a maximum of 110 decibels. And we actually measure that 12 inches from the siren itself. So you can kind of get an idea of that decibel rating. So there's one particular characteristic of sound that is a little more challenging to understand, but it's very important to the use of sound for airway clearance. And that is called resonance. And while resonance exists in both the mechanical pressure wave spectrum and the sound wave spectrum, the 2 are very different from each other. The last bullet point on this slide says any sound generated, no matter how it's created, generates both harmonics and subharmonics. This is another topic that's a little bit difficult to understand because we typically think of creating one sound, and it really doesn't work that way. We create many sounds when we create one, and we'll look at some slides that help us to understand that. So if you look at sound in medicine, this is not the first time that sound energy or sound waves have been used in medicine. I spoke about that sound spectrum a few moments ago, and it goes all the way from infinity on the bottom to infinity on the top, realistically. However, there are different bands of sound, sound energy and sound frequencies that we use for different things. Most people are familiar with the ultrasound frequencies. Ultrasound is typically used to bounce sound waves off of different things through fluids typically, and then measured on the return waveform. And then you can create an image by how much or how little is returned to the receiver. We're pretty familiar with that, so we can image a baby in the womb. And it also highlights another point. The womb is liquid filled, and it uses the property I mentioned earlier that sound moves differently through different mediums. So in that scenario, the sound waves are moving through the fluids and not necessarily through the open air or into a particular space or cavity. So we're familiar with that. The next range that we're all familiar with is the audible sound range. When we are born, our ears are typically able to convert sound waves from 20 hertz or 20 cycles per second all the way up to 20,000 cycles or 20 kilohertz is the way we term that. And they convert that into information that's passed on to our brain so we can interpret it. But as we age, our ears in that range of hearing, it decreases naturally as we age until we get to the later parts of life where the sound frequency capabilities of the ears can narrow significantly. Most people will lose the higher end of the spectrum and lose the higher frequency sounds, but some people lose the lower end as well. The frequencer is a product that uses a frequency band called infrasound. Infrasound is sound waves that are below our hearing. While we can't hear them, there is sound that often is produced by this band, and that is a byproduct of usually the transducers that are converting electrical energy into sound energy. So it's kind of a waste sound. We'll hear it, but that's not the sound that we are using to do work within the body. So that we call infrasound. And on the higher side, there's a lot of other medical therapies that have, and I'm sure there will be sound products for years and years to come as we gain knowledge. So learning about sound, the topics of harmonics and subharmonics can be very challenging to learn, as well as resonance. So we need to spend a few moments to try and understand those principles. And the reason is because that is what we're going to use, are those characteristics about sound to help us. Typically, we create sound with electricity, and then a transducer converts that into an electromagnetic waveform that either we can hear or does some other type of work for us. When that happens, we create what we term as a center frequency. And on the drawing there, the little graph scale, I chose 440 hertz. Okay, 440 hertz is in the hearing spectrum of our ears. So if I were to create that frequency and apply it to a transducer, it would be in my hearing range. As a matter of fact, that is one of the frequencies that we used to call dial tone on a telephone. For the people on the webinar that have used a home phone, you would pick it up and the phone company would use a tone to let you know that it's ready to dial. And that tone in the US was 440 hertz. But when we create a 440 hertz sound, we also create every multiple and every divisible of that. So you can see in the drawing that when we created 440, the first harmonic up is 880. So we also create that sound. When we look at the lower side, we also create the divisible, which is, of course, 220. And that multiplicand and division goes all the way up the scale and all the way down the scale through eternity. It's not possible to create only one sound frequency. But if you'll notice on there, the power side of the chart shows us that the harmonics of the originally intended wave are lower in power than the original waveform. And I have a chart that shows this. So if we create a frequency of 440 at 100 decibels, the first harmonic up would be in yellow there, and you'll notice that the power is only 30.3 decibels. Likewise, the next harmonic up drops down to 2 decibels. So the power rapidly decreases as we move away from the center frequency that we create. This is important because when dealing with frequencies, we are often not dealing with one specific frequency. And we'll discuss that more in a couple of slides, but we are dealing with an approximate frequency most of the time. So we know, as I mentioned, sound is amorphous. It moves. We know this because if you're outside across a parking lot and you yell at your friend and say, hello, they can hear you. We know that that sound pressure wave that we generated with our mouth moved across that parking lot and reached that person's ears. So that is a characteristic that we know happens, and it moves differently based on the medium it's in. Okay, so if it's in sound waves in water, move different than sound waves in air. It also moves differently based on the shape of the container. So if we're in a triangle shaped room and you're in one of the outside edges nearer to the walls, when that person in the center of the room speaks to you, those sound waves are going to spread out, but they're going to collide with each other as they come back. And because you're in the corner of the room, you will hear more. The power in those sound waves is condensing down and will be stronger in the corner. So there's some characteristics there that we don't necessarily use, but it's important to understand. The other property that we discussed is resonance. Resonance is also termed sympathetic waveform increase in the engineering world. And it's the frequency at which those reflections of sound waves and returned or bounced waveforms all collide at just the proper space, and they increase the power by blending together. So the importance of this is there is one specific frequency that is for each container of sound, each medium of sound. The size of the container all the other characteristics that create the container of sound, there's one frequency that is called its resonant frequency. Okay, and when you achieve that resonant frequency, the sound will increase its own power, and it continues to do that until it runs out of energy. And this is also a property that we deal with in mechanics or mechanical waves. So at the end of the video, I will show another quick video. I mean, at the end of the webinar, I'll show a quick video if we have time, that when we build mechanical structures like a bridge across a river, we have to build in what they call resonance dampers. They're engineering controls that make sure that nothing can create a mechanical wave or a vibration or movement that reaches resonance. Otherwise, it will reproduce and re-strengthen itself with its sympathetic waveform increase to the point that it destroys the object and the container it's in. So the video that I'll show you is an example of a bridge that was built back in the early 30s and 40s. It was constructed, the engineers left out all the concepts of resonance, and shortly, a couple months after it was open to car traffic and all, the wind blew just at the proper speed and caused a vibration that hit the bridge's resonant frequency. When it hit that resonant frequency, the sympathetic waveform increase started in this bridge that crossed the Tacoma Sound, actually up in Washington, started to shake and vibrate more and more rapidly until the bridge actually destroys itself and falls into the river. So that's a mechanical form of resonance. We're a little more familiar with a sound form of resonance, and that is the singer that can hit notes that actually achieve resonance, sound waves that get inside of a glass. When they're at that exact frequency, the sound waves start to increase in power and actually increase till they get to the point where they explode the container they're in. The glass can no longer withstand the pressure, so the glass breaks. And we've seen that. There's a lot of other examples, but if you ever just want to see that, you can go to YouTube and just type in resonance and sound or resonance and mechanical, and you'll find many, many other examples of that. So with that being said, as it relates to sound, every container has a resonant frequency for sound. It also has it for mechanical, but it's not something that we're going to use, and it's a lot harder to achieve a mechanical resonance as opposed to a sound resonant. So if we look at that and we're going to clear the lungs and the airway system, we need to know what the airway system's resonant frequency is. There was a United States Navy study that looked at how sound worked with the lungs, and they used sailors in a submarine to do their study. The actual fear was that another country would be able to create a sound wave that would get to the soldiers' lungs. And if they created resonance, they originally thought that it would explode the patient's lungs. That wouldn't happen and didn't happen. But during that study, they were able to determine that the resonant sound frequency of the human lungs is about 40 hertz. Earlier, I mentioned we don't really deal with exacts and specifics, and you can easily understand why we can't use specifics with that, because our lungs expand and contract as we breathe, and that expansion and contraction can and will change the resonant frequency, but it's about 40 hertz and it doesn't change it a lot. So we know if we stay in the 38 to 42 hertz range of sound wave energy, that will hit the resonant point for the lungs. So there's a couple other things that we can look at that help us understand the resonance example. We know that energy sharing between two objects that have the same resonant frequency takes place easier than anything else. An example of that is we know that a guitar has a string on it that creates a sound that is an E note. It'll have a certain frequency, and I'm not certain. I can look it up and see what frequency that is. Doesn't really matter in our example. We also know that a piano has a string in it that creates the same note as an E. If you hold a guitar up next to that piano and you strike the E key on the piano, causing that frequency of sound, and then you look at the E string on a guitar, it will be accepting that energy because that is its resonant frequency as well, and it will vibrate. It will actually vibrate more than any other string on the guitar. As a matter of fact, this came from a Massachusetts Institute of Technology study where they looked at energy sharing. And that was a study that looked at how we can use resonance to share energy between two objects. We're going to do that. Method one that I mentioned earlier is we're going to create a sound wave and put it into the lungs, and it's going to share that energy with the lungs. So they're going to accept that energy, and that's going to help the cilia move and do what it does better. So we'll see that in a few moments, but that's an example of how resonance and energy sharing works. So back to the body, we know that the lungs has a frequency of somewhere in the 38 to 42. The study said 35 to 40, and it's been measured, and you know, I'm not sure you could ever get to an exact, but it's about 40 hertz. And we know that if we're going to use sound energy, we need to be in that range. Mechanical waves, however, for instance, when we cup on a patient, some people call it clap, but when we use our hands and create mechanical cupping by striking a patient, it creates a mechanical waveform, but we can't really get to the resonant frequency of the body. And because of that, we know that those waveforms create a strong pressure waveform on the outside of the body, but they diminish rapidly as you move inward toward the center of the body. So when we do that, those waves, even acoustical waves, are weaker on the surface than they are internally. But we do know that sound waves can pass through the body much easier and will actually come out the other side with very little reduction in power. So we can actually measure that and tell that we don't lose much of our power like we do with mechanical energy where we strike a patient, or like with the vest where it is inflating and deflating, causing mechanical pressure, or a percussor that we hold on the patient. That again is mechanical energy, and the body absorbs it. The body has to be designed that way. Otherwise, every little bump or accident that we got in would cause tremendous damage to the organs inside. So that's a little bit about the body. We know that when we do cup or clap, that mechanical energy is about 4 to 6 hertz, or 4 to 6 times per second. It's about all you can get to with your hands. and the power or strength of it is limited because you can't really just hit a patient really, really hard. So you can get to where you can hit them hard enough for it to go through the body and be felt on the other side, but it would obviously injure the patient. So it's nothing that we would do intentionally. So we look at the frequency of other devices, and there's a lot of different things out there with the percussor and the vest. They both have controls typically where we can vary the frequency at which they create a mechanical wave on the surface of the patient's body. So most of them run at about 12 to 20 hertz of mechanical energy. And there's all kinds of different studies out there as to what frequency is best. If you've ever been in a sales scenario, the sales rep probably has studies that the company has done for like the vest or the frequency that, that fits their product best and all. But either way, even we can never hit the mechanical resonance point. And we know that those waveforms that are being created don't go very deep into the body. And this is just a graphic that shows us the body absorbs large amounts of that mechanical energy, but sound penetrates through the body. So we'll see that, we'll use that with the frequencer. One of the ways that we set it up at trade shows and all is you can actually put the transducer on the patient's body and put your hand behind it on the back of their body, and you can feel the sound waves coming through. So like I said, you can do that with mechanical energy as well, but not very much. And you would get to a point where you actually can hurt the patient. So to kind of sum that portion of it up, if we use sound for helping with the lungs, it would be best at the resonant frequency, or at least around the harmonics, the first harmonic up and harmonic down, subharmonic of the 40 hertz signal to help us share that energy and do the work. At resonant frequency, the energy transferred to the lung will cause a vibration in all of the structures, and the cilia will move easier. When the cilia moves easier, if you remember from our part 1, it will alter the physical shape and size of the mucus. And when it does so, the mucus will naturally thin, and that will make it easier for the cilia to move the mucus into the larger airways. The other thing that's important to remember is that sound gets through the body, whether it's a large airway or a small airway. So that is an important concept that we need to remember. The second method that we're going to use is what the sound wave does to mucus. We ended last week's session with a video that showed us how the material that was like mucus acts when sound waves at a resonant frequency get to that material. It alters its shape and size, and then the viscosity is reduced and the material gets thin, which is our hope. That's what we want to happen with the mucus. Especially 40 hertz is a very low frequency, and the experiments that were done used the low frequency. If you'll remember, it's a non-Newtonian material, and that sound, when we get to that, causes it to move and distort its own shape, thinning it, and by its viscosity reducing, it moves easier. So if we want to take a look at that, I'm going to show the video again. It takes about 60 seconds, so bear with me. And notice that the material you see on your screen now is very thick, and watch how it turns to thin, runny material. Okay, so it's important to also note that the sound you were hearing is not the sound frequency that was causing that material to do what it did. It was a frequency that was generated below our hearing that caused that action. Same thing can happen in our lungs. So let's talk about the product that we have in the frequencer. It's an FDA product that can help us use the principles that we've learned about. We've learned about physiology and we've learned about sound. So let's look at the product and how it works. Firstly, the frequencer was developed by the person you see pictured. His name was Louis Plant, and he had cystic fibrosis. He was also an electronics student studying to be an electronics engineer, and learned a lot about the principles that we've been talking about. He liked rock concerts, and I have never met him, but I understand it was often hard rock music that was very loud. And he realized that when he was close to the speakers, something would happen within his CF, his excess mucus, and it would cause him to cough, and he would feel a difference in the mucus. So his goal was to figure out how that worked medically and create a product that would replicate that without the volume that would obviously be damaging to your ears. We could have made a frequencer really easy just by getting a huge set of speakers and turn the music up real loud and standing between them. Problem is we would be deaf, of course, by the time we fixed our mucus condition. So the frequencer was a product that came out of that. This is a picture of the frequencer. You'll notice that on the screen, there are adjustments for frequency. There are adjustments for power, and there's a start-stop control. And on the left side, you see the transducer laying in its cradle. The transducer has a filter that goes on it. The filter is there to protect the patient and the machine from bacteria and other bodily situations, issues. But the filter also has a material in it that is designed to not block or impede the sound going through it. The usage is simple. You will see later in this, where we want to put the frequencer transducer on the patient. And the best scenario is to seal that circle on the patient so that the sound has nowhere to go. We know it moves, and it moves like gas or like water. It's going to take the path of least resistance. So if you put the transducer on the patient and lean it up where it's not sealing on one side, you lose a significant amount of the sound out of that opening. So it's gentle to the patient. And just to give you some ideas, when we press it on a patient to seal it so the sound goes into the patient's body, we are using about 1.8 newtons of pressure. 58 newtons is the average amount that we use when we're cupping or clapping on a patient with our hands. So there's a big difference there in the external pressure on there. The frequencer is a quiet machine in therapy. You will hear noise when you are using the frequencer on a patient. Remember, the noise that you hear, just like in our mucus video moments ago, that's not the sound waves that are helping the patient. They are below your hearing capabilities. So just keep that in mind. The operation of the total machine laying open like it is right there is 65 decibels. So while that may sound loud, it's really not very loud. Sound is a logarithmic thing. So even though 65 sounds like half of a fire siren or a police siren, it's not. And if you ever turn one on, you'll barely hear it. It's more like a hum or a buzz. Standard uses of it, as I mentioned, are to put the transducer on the patient, seal it. A towel or a thin cloth, a t-shirt works well between the patient. It actually, where we put it on, it could cause a little red ring that does nothing. It goes away just seconds after you take it off. But the t-shirt or towel prevents that, but it still directs the sound into the body. And we know from what we discussed earlier, that sound moves through the body, getting to those smaller, tinier airways like no mechanical therapy can. To use the device, it's best if the patient either sits up straight or slightly leans back in a hard chair, but it can be used on a patient laying down in a bed. So there's some ways that are best, and they all work. If a patient's in a bed and they are even laying supine flat, you can still put the device on the patient and get the sound into their lungs by putting it on there and sealing it. It can be used on the back or the front. So you get your patient in the treatment position, and then you would select the proper size filter. The largest filter that you can seal is the best filter. There's 4 different sizes because this works extremely well on pediatrics, and there's even a neonatal filter that's not pictured. The neonatal filter, it looks like a filter backwards. It attaches to the transducer and has a tube that's about 1 inch wide that goes off to a rubber end, and that rubber end actually goes on the neonate to get the sound into the patient's body. Then we select the proper power level and frequency. The power level is a function of comfort. And while we don't see many patients that are uncomfortable with it on high, most patients like it. It's kind of like getting a massage or something. So it may be turned all the way up on every patient you use it on. It has very little effect on how much the treatment works or not. The frequency, however, the way we adjust that, we typically use 2 methods. The first method is, as I mentioned earlier, we will put the transducer on the patient, seal it on their upper chest, and then put your hand on the back side of the person's back, and you will feel that sound coming through, and you can adjust it that way. The best way we've found is to have the patient talk or make a sound, a tone or a hum for us, and adjust the frequency to where we get the most effect on their voice. So that's something, if you ever get a frequencer in front of you, you can kind of play with. When we get that maximum vibration effect or Darth Vader effect in the voice, whatever you want to call it, that's where you are at or close to the resonant frequency. Okay, once we do that, it's as simple as applying the filter to the patient's body. And there are 6 locations that we use. Some people will treat 4, some people will treat all 6. The therapy, quite honestly, if you put it in one location and held it there for the entire treatment time, it's not really treating that one location. It's simply stronger in that location. So you're treating the entire chest if you're treating, or the entire chest area if you're treating any position, because of the way sound moves through the body. But we do know there are things like mucus plugs that appear in certain areas, so we can highlight the therapy by moving the transducer to those areas and specifically treating those areas. Then you just simply turn on the machine or activate it so it works. The directions for use tell you to move the filter every 2 minutes, but again, that's up to the person doing the treatment. There's really no contraindications to even leaving it in one spot. So there's a lot of different ways that I see people using it on patients. That is the end of this portion of the presentation. And we are right at almost at the 10:45 point. So I wanted to show you the video that I mentioned earlier that shows the bridge and what happens when that bridge reaches a resonant point. Joanne, can you confirm for me that you are seeing that on your screen?
I do.
Okay, so I'm going to start this video. And while I'm starting close to the middle, the first part of it just goes through the dates and it shows a parade that they had opening the bridge and everything. So the wind was blowing this particular day and it started to vibrate and sway at a resonant frequency. You can see the mechanical waves of energy hitting that sympathetic waveform increase point we talked about, and they get larger and larger and larger. And this is actual video of the bridge. Fortunately, the losses were minimized because, as you can see, there was no one on the bridge. There was one car and everybody else got off of the bridge. Yeah, that person risked his life to get his dog out of his car. I probably would have done the same thing. As the waveform increases itself over and over and over, the bridge's structure is getting weaker. And we will get to the point here shortly where the bridge will actually disintegrate. It's almost like they're showing you an experiment, but it was totally unsuspected and predicted. The engineering company just made a mistake. And I believe it said $6 million is what that cost to build, which in today's money, that was 1939 or 40. So that was an expensive mistake for someone to make. So we're at the end of our time. And as Joanne mentioned, we'd like to entertain some questions.
Okay, so thank you so much, Don, for a really good presentation and for ending with the bridge. I think that was pretty compelling. So as I mentioned, please enter your questions in the Q&A panel. Don, if you can quickly answer this question, can you just reinforce, because I know we just did it with the bridge, reinforce the difference between sound resonant frequency and mechanical resonant frequency in the lungs?
Oh, yes. The bridge that you saw was a great example of mechanical resonance. Sound resonance occurs like in the glass. The sound waves get inside the glass and they start to reflect and bounce. And the bridge, it was the swaying, the mechanical, that just got more and more and more. In the glass, the sound waves, you can't see it, but they're doing basically the same thing. They get stronger and stronger and stronger until the container can no longer hold it in, and the container that the sound waves are in shatters in the glass example. So if we can create that type of resonance in the lungs, those sound waves that get stronger and stronger and stronger create the reaction in the mucus. So with sound, the only difference that we have is, since there's not a mechanical functions to it, sound eventually does run out of energy. Unlike the bridge, it ran out of energy when the bridge fell. So we don't get that within our lungs because the sound is not limited within that space like it is within the glass and all. So that would be kind of the difference in the two types of resonance.
Okay, thank you. We also have a question from an individual who said they had a patient who they couldn't hear the vibration in the voice when using the frequencer. What do you think caused that?
Most likely, if you'll remember, the shape and size of the cavity can alter and will alter the patient's resonant frequency. And when we say 40 hertz, it's about 40 hertz. As I mentioned, as we breathe and the lungs expand and contract, that changes the resonant frequency, however, not significantly. If you probably had a patient that had enough secretions, enough mucus in their lungs that it altered the resonant frequency to the point where you could not achieve its resonant frequency. The frequencer has a range of adjustment, and you probably just fell outside that particular range. I treated a patient one time that had one lung. Basically, when you have one lung, it's and actually had I'm at a loss for the word. The bottom portion of the lung had been removed. And when you do that, it alters that resonant frequency. So to achieve resonance on that patient, it would have required us to go up to about 50, 60, or maybe even 65 hertz. But remember that it's not a reason not to treat the patient, because the harmonics in the subharmonics are still going to be able to get close enough to cause reactions within it. They're just not as strong as what we've seen in the videos if we're able to achieve a direct resonant frequency. Most likely something changed the resonant frequency of the lungs, so you were not able to achieve that.
All right, great. Thank you for that. And then we have another question, but this one's more on intensity and the safety of the device. And the question is around increased intensity doesn't harm a patient outside of the recommended levels. The question is, it's a little choppy for me, I'm sorry. The question is related to neonates, basically increasing the intensity. So why don't, if you can, talk about intensity levels and tolerance.
Okay, certainly. I've never experienced a patient that couldn't tolerate the frequencer on high. And as I mentioned earlier, most adult patients think it feels like a massage. The way the sound works within the patient's lungs, the lungs are not like the glass that you saw. In the glass, the sound goes into it, but was unable to exit the glass. And when the pressure got high enough of the sound waves and their strength, it exploded the glass. When we use it on the lungs, even though we achieve resonance, it builds the power and builds the power, but the sound wave is also able to escape through the lungs. It's not like a hard shell. So you can never get to the point where you're going to cause a physical damage scenario like you saw with the glass. Unfortunately, neonates couldn't tell you if they liked it or didn't like it, although some of their reactions show that they do like the vibration. Some of the babies do, some don't. But there's no potential for injury just because it's not like a solid container or shell that's containing that power in those waveforms. Does that make sense? I think we might have
Yes,
lost.
Don. Yeah, I muted myself. I think it answered the question. I don't see any additional questions coming through the panel. So do you have any final remarks that you'd like to make before we close this out?
Yes, before we leave that topic of the potential injuries, there are none that we have found so far with the product. The FDA didn't find any potential injuries or negative byproducts of it either. But one thing that I often get asked is, it came up in a session not too long ago about, is there the potential to cause, for instance, dysrhythmias with the heart? And it's not, because the heart functions off of electrical energy that flows through the proper tissues in the heart. And sound waves don't mix with or affect the electrical energy at all. It's two different types of energy that cannot affect each other. So just wanted to mention that has come up recently in a thing. So I wanted to bring that out.
All right, great. Well, thank you for that. And for really this two-part series, we really appreciate your time, efforts, and energy in presenting to our customers and our partners. So thank you so much.